Okay, pre-calculus, we are going to do lesson 5.2, angles and their measures. So here we go. This should be mostly review for you. There are multiple ways to measure angles. We can use degrees. We can use revolutions, which is maybe what's new here. Bearings, maybe that's new too, and radians, which is not. You learned that last year. Okay, degrees. From geometry, a straight angle is 180 degrees and a circle is 360 degrees. Revolutions. One revolution equals one full turn around a circle, which means one revolution equals 360 degrees, or one revolution equals 2 pi radians. Radians. An angle of 1 radian is defined to be the angle at the center of a circle which spans an arc of length equal to the radius of that circle. So you kind of have the picture here. Here's your radius of your circle. And this arc length here is also r. And when that arc length is r, then you have 1 radian. Let's see. All right. Please keep in mind up here with degrees that if we're talking in degrees, you must use the degree sign. If you do not use the degree sign, then it is assumed it is a radian. So keep that in mind. Okay, to measure an angle in the most precise way possible, we sometimes write it in degrees, minutes, and seconds. Each degree is made up of 60 minutes, and each minute is made up of 60 seconds. So we can use a calculator to help us convert to DMS and back. DMS, degree, minutes, seconds, and back. So let's just do this. I'm going to try this, minimize my screen, and there's my little calculator. We'll see how this works. Not really how I wanted to minimize it though. I kind of want to not have it go off. So maybe if I shrink it first and then minimize it. No, same result. What a surprise. Oh well, we'll just do the best we can. Okay, so let's do this first one, example 1. We want to go from degrees, minutes, and seconds to decimal degrees. So right here, we have no decimals. We have 32 degrees, 17 minutes, 12 seconds. So what we want to do is we want to take all that and change it just into decimals. So what you'll do, I'm just going to write it down at the bottom here where I have more space. You're going to say, okay, I have 32 degrees. And then I also have, so plus 17 minutes. But I know that for every minute, 60 minutes is 1 degree. So we're just going to do these little unit fractions here. So then our minutes cancel, and I have changed 17 times 1 divided by 60. We'll change that into a decimal, plus. Then I also have 12 seconds. And then my little conversion there will be, well, I know there are 60 seconds in 1 minute. And then I know there are 60 minutes in 1 degree. And so the minutes cancel, the seconds cancel, and I'm left with all degrees, degree, degree, degree. And so I just have to do that math. So pulling up my little calculator here, I'm going to say 32 plus 17 divided by 60 plus 12 divided by 60 times 60 is 3,600. And that is going to give me 32.287. Or you could say 32.286 with a repeating. But since we are in general rounding, well, always rounding, then we're just going to say 32.287 degrees. So, I wrote all this out for you just so you can visualize it, but really what you're going to do is you're going to say 32 times plus 17 over 60, dividing by 60 will change from minutes to degrees. And then here you're going to do your seconds divided by 3,600. And that will give you your decimal degree. Okay? So doing it the other way now, in example 2, we are given it in decimal degrees, and we want to convert it to DMS. So first of all, the 47 is your whole number. So the 47 stays as 47, right? And then we have this 0.26. So let me just get another color going here so that we can keep these problems separate. So you're going to take that 0.26, which is in degrees, and this time you are going to multiply it by, just remember that's in degrees, so then you're going to say, okay, that's degrees. 1 degree is 60 minutes. And those degrees cancel and you're in minutes. And when you do, off on your calculator, you do 0.26 times 60, you're going to get 15.6. And so that, you're going to take the whole number portion of that, and that's going to give you your minutes. So we have here 47 degrees, we have 15 minutes, and now the remainder of that 15.6 over there on your calculator, you take that decimal that's left, 0.6, and now you're going to do that, and that is in minutes. And so now we want to go from minutes. 1 minute has 60 seconds. So now you take the 0.6 that's left, because those minutes cancel, 0.6 times 60, and that's going to give you your 36 seconds. And there's your answer. Okay? And notice how it's marked. This is degrees, this is minutes, the 1 dash, the 2 dashes is seconds. So there you go. All right, I'm going to erase that. And standard position. You can remember this. We did standard position a lot last year. Hopefully you remember this with a smile, because it's not so bad really. It's taking a while though, sorry. Hopefully, fast forward, my erasing. Okay, good enough. All right, so standard position. For degree angles, revolutions, and radian angles, we draw the angles with their initial side along the positive x-axis. So remember that. Oh my. Whenever we did this, this was the initial side, remember? So we draw, I'll just label that, initial side. And then the terminal end side of the angle is then measured in a counterclockwise direction. So like for a 45-degree angle, here's my initial side, there's my terminal side, and that would be a 45-degree angle. That is in standard position. If we were doing it, well, let's do another one in degrees first, because I think we all kind of still think in degrees. Let's say I wanted to do 290 degrees. Well, my initial side is right there. This is 90. This is 180. This is 270. So 290 would have my initial side there, and then it would go all the way around to like that. And that would be my 290 degrees. Remember that the negative means we're going in the other direction. So, all right. Reference angles. So now when we put these angles on, reference angles are very important when we're dealing with standard position. Reference angles is the acute angle, it's acute, between the terminal side and the x-axis. So for example, for my 270 degrees here, the blue is the 270 degrees, but it leaves this little reference angle. That would be my reference angle for 270 degrees. The measure from this initial side to the terminal side. And if you remember last year, we talked about the bow tie. Reference angles are somewhere in this bow tie. So it could be, this could be the reference angle, or this, or this, or this. It is always made by the x-axis and the terminal side. All right, so then draw the following radian angles, then list their reference angle. So I can actually make this big and have a little more space. But I get to erase again. Erase. Okay. There we go. So let's do the first one. Pi over 2, if you remember. Here is 0. Here is pi. Going all the way around, then this would also be 2 pi. That leaves pi over 2 is right here. This is 3 pi over 2. You just kind of have to know those numbers. So to draw this angle, we have our initial side there, and then we go up to pi over 2. So you would just say this is pi over 2. Now, this is called a quadrant angle. And this isn't in your notes, so make sure you write it down. A quadrant angle is an angle on an axis. An angle with terminal side on an axis. And therefore, because, technically our quadrant angle here is here and there is, now remember, for a reference angle, it has to be an acute angle. That means it has to be 90 degrees. Well, there is no reference angle here. So quadrant angles have no reference angles. So make sure you take note of that, okay? Moving on to 11 pi over 6. So this is pi over, well, this is 0. And this is 2 pi, which would be 12 pi over 6. You want to get the same denominator, and so for 2 pi, it would be 12 pi over 6. And once you have the same denominator, it's a lot easier. Over here, this is pi, which would be 6 pi over 6. This is pi over 2, which would be, 3 pi over 6. And then this one down here would be 9 pi over 6. So whatever this little denominator is of the angle you're trying to put on in standard position, get all those common denominators, and then you know that your angle, here's your initial side, and then the terminal side for here is going to go all the way around to about, more, there, right there. There is the angle in, what is that, orange, of 11 pi over 6. But then the other question is find the reference angle. So remember the bow tie, which is right here. One of those is the reference angle. So in this case, this is my reference angle. So what is the measure of that? Well, the question is, this is 11 pi over 6. And then to get to the axis is 12 pi over 6. So theta reference is going to be pi over 6 in this case. Okay. Next one, 4 pi over 3. So again, a full circle in this case would be 6 pi over 3. This over here would be 3 pi over 3. So 4 pi over 3, just to go on with that, if we want, this would be 4.5 pi over 3, and this would be 1.5 pi over 3. But anyhow, 4 pi over 3 is going to take us, here's our initial side, and we go like this, and we get pretty close to here, and this is 4 pi over 3 right there. And now the question is, find the reference angle. So remember, the reference angle is always with the x-axis, not with the y-axis. Therefore, this is my reference angle. Reference angle is always with the x-axis. And so what is the measure of that angle? Well, if this is 3 pi over 3 and this is 4 pi over 3, then theta reference is going to be 1 I'm sorry, if this is 3 pi over 3 and this is 4 pi over 3, then theta reference is pi over 3. Okay, and then now the last one is 2.9, and that is radians because it does not say degree. And so we are going to graph that. Keep in mind that this is pi, and let me put another color in so we keep it all separate, even though it's pretty chaotic. There we go. Okay, this is 0, this is pi, and we know pi is approximately 3.14. This is pi over 2, which means this would be like 1.57-ish. Just kind of winging that. I hope I did that math right. But anyhow, 2.9 would be right over here somewhere. So here's my initial side, there's my terminal side, and there is 2.9 radians. So theta reference is always made with your x-axis and your terminal side. So there's theta. And theta reference in this case, if this is 2.9 and this is about 3.14, then theta reference is going to be about 2.5. Just looking at that. That's what I have down in my notes. I got to bring up my calculator. 3.14 minus 2.9 is 0.24. I don't know where I got that from. 0.24. There we go. Okay. Which is actually what I had in my notes, not 2.5. I don't know where I was looking. All right, so now to the next page. We can convert some radian measures to degrees in our head. For example, pi over 2 is 90 degrees. So that should be something that you just know. Other common ones, pi over 4 is 45 degrees. You should know that. Of course, pi is 180 degrees. 2 pi is 360. There's some others. We'll get to 30 and 60 later on. So anyhow, we can convert some radian measures in our head. For example, pi over 2 is 90 degrees. But sometimes it is easier to convert using the fact that pi radians equals 180 degrees. That's your little conversion. So remember, when using degrees, you must use the degree symbol. So convert from degrees to radians or radians to degrees. So this one is 200 degrees. I want to get to radians. Right here is my conversion fact. So I'm going to say, all right, 180 degrees is pi radians. And so you always want to line it up in such a way that your units cancel. So you have 200 times pi divided by 180. And since we are in radians here, we don't really want to have those decimals. So you're going to simplify that, 90, or what should we say? 20 goes into that 10 times. 20 goes into that 9 times. So we would say we have 10 pi over 9 radians. Now going the other way, this is in radians, we want degrees. So in that case, line it up, you want your pi's to cancel. So I'll say pi radians. You don't really need to write that radians, it's just assumed is 180 degrees. So the pi cancels, the radians cancel, and so then you are going to get 315 over 2, and there you can yank out your calculator and you get 157.5 degrees. So keep in mind, in general, when we're going to radians, we just want like a nice little fraction. But when you go to degrees, you can use your decimals. All right, arc length. The length of a portion of the circumference of a circle is S equals theta radius. So you need to know this. This is our arc length formula. And if you remember way back to geometry, when we did not know radians, this formula was way more complicated in degrees. It is way easier to use it in radians. So this measure right here is where S is the arc length. So here's your arc length. And theta is the angle, but it's not just any angle, it's the central angle. Or it is the measure. Remember back to geometry, if we have this angle, this is the center of the circle, here's a radius, here's a radius. This angle right here was called the central angle. But remember, the central angle, this measure right here, is also the measure of this arc. It's not the length. There's two different ways to measure an arc. One is like the curvature, which would be the degree, so the arc measure. The other one is the arc length, which is what we're talking about. Like if I took this curve and I straightened it out, how long is it? Sorry, my kids are all calling me right now, but I just hung up on them. So, okay. Anyhow, and R is the radius of the circle. So this formula is way easier, and we're in radians here. So this is the central angle in radians. If you go in degrees, it's a lot harder. So we always want to change to radians when we use this. Example 5, find the length of an arc. So here's our formula, S equals theta times radius, which means I have 5 pi over 6 times 4. And that is going to give me 10 pi over 3 centimeters. The length is centimeters. Okay? Next one. This time we are in degrees, so to find our arc length, we're going to say, okay, I have 125 degrees. Well, the first thing I want to do is I want to get from degrees to radians. And so now my degrees are gone. Now I'm in radians. Now I can just multiply by my radius, which is 1.5, and this would be 25 pi over 24 millimeters. That's how long that arc is. Example 6. 5 streets come together at a traffic circle. The diameter of the traffic circle is 200 feet. So D equals 200 feet. The traffic flows, and so radius is 100 feet, by the way. Okay, traffic flows counterclockwise. What is the distance from E Street to Neponset Street? So E Street is right here. Neponset Street is right there. And so we are trying to find this distance. If I'm driving in my car, what is the distance of that arc? So what are we going to do? We're going to say, all right, well, first of all, we have to know the central angle measure. So this portion is 90. So theta here is going to be 90 plus this portion here. And that portion here would have to be 50 because this is 40, and together those make a 90-degree angle. So I have 50 plus 90 is 140 degrees. So then my formula is arc length is the central angle times the radius. And so we are in degrees, so I'm saying 140 degrees times 180 degrees over pi. So now I'm in radians times my radius, which is 100 feet. And so take out your calculator and you do that, which I'm going to do because I think I have another mistake in my notes. So I have 140 times pi times 100, all divided by 180. 244.346. 244.346 feet. There's my answer. The notes are wrong. If you look at the answer key of the notes, I'm not really sure where I got that. I even have the answer in centimeters, which is very strange, so I don't know what I was doing. But regardless, moving down, angular and linear motion. Angular speed, how fast something is spinning. That is talking about the revolutions or radians per time. How many times does it go around during a certain amount of time? Whereas linear speed is how fast something is traveling in one direction. So that is the distance per time. Miles per hour, whatever that might be. Okay, example 7, a turntable rotates 50 revolutions per minute. What is its angular speed in radians per second? So as you do these problems, you want to start with your given ratio. I know you guys like that better. But anyhow, so I am given that a turntable rotates 50 revolutions per minute. So that's going to be where I start. I have 50 revs per 1 minute. That's where I'm starting. What do I need to get to? I want to get to radians per second. So, first of all, let's take care of the time. If I have 1 minute, then I have 60 seconds. So the minutes are gone, and I'm down to seconds. Now, the next thing is I need to get from revolutions to radians. So in one full revolution around a circle, one revolution, that means I've gone 2 pi radians, right? Just like if I am riding my bike and I go a full circle on my wheel, and that means I did 1 revolution is 360 degrees, right? That's what 2 pi and 360 are the same thing. So now there's another unit multiplier. So I can say right here, 1 revolution is the same as 2 pi radians. And so the revolutions cancel. What am I left with? Radians per second. That's what I want. So I do my math. Again, let's just simplify, and you should end up with 5 pi over 3 radians per second. Okay, next one. A car that is traveling 42 miles per hour, so that's my starting point, has a chalk mark on the tread of its tire where there is a small nail. If the tire has a diameter of 2 feet, which means the radius is 1 foot, right? What is the angular speed of the nail in revolutions per minute? All right, so I'm going to start with what they give me, 42 miles per 1 hour. I want to get to per minute, so let's take care of that first. 1 hour has 60 minutes. All right, so I'm per minute. And then I have my radius is 1 foot. Now, off to the side here, let's talk about this. A revolution is the arc length when you go a full circle, which in this case, circle. A full circle is 2 pi, right? If I've gone a full circle, I've gone 1 revolution. What's the arc length of that? So what's our formula for arc length? S equals theta times radius. So the arc length here would be S equals, the full circle is 2 pi, and then what's my radius? 1 foot, right there. So therefore, 2 pi feet is the arc length for 1 revolution is 2 pi feet. So I'm going to use that fact, and I'm going to say I need to get to feet here, right? But what I have is 1 revolution equals 2 pi feet. That's another unit fraction I can use. But first we got to get from miles to feet. So hopefully you know that there is 1 mile has 5,280 feet. And therefore then I can use this because I have my feet, and I can say 2 pi feet is 1 revolution. And that's what I want. So my miles cancel, my feet cancels. I am left with revolutions per minute. Yay. use your calculator, multiply, divide, and you should get 588.237 revolutions per minute is your answer. And there you go. You're going to do a bunch of little story problems, and you're going to do a bunch of angles in standard position, and you're going to find the reference angle. Remember the bow tie when you do that, and that's it.